Hi, I'm Christine Hertzog. I'm Managing Director of the Smart Grid Library, and here with me today is Terry Oliver. Terry is the Chief Technology Innovation Officer, CTIO, and he's with Bonneville Power Administration. And so welcome today, Terry.
Thank you.
I'm glad you could join us here. And first and foremost, if you could give a very brief description of Bonneville Power Administration, and then tell us about the role that Bonneville has within the Pacific Northwest Smart Grid Demonstration Project, which is a very interesting transactive energy project.
So Bonneville Power is one of the power marketing administrations within the U.S. Department of Energy. We serve the 4 Pacific Northwest states: Washington, Oregon, Idaho, and Montana. We're the operator of the bulk transmission grid, and we also sell the electricity that comes off the Federal Columbia River hydro system that's actually owned by and operated by the U.S. Army Corps of Engineers. So we wholesale electricity and we provide transmission services, 2 fundamental businesses that we're in. We also do a major investment in a new resource, new as of about 30 years ago, but still foreign to a lot of utilities, the idea of energy efficiency as a resource. It's actually the 3rd largest resource in our system now. We provide a social benefit to the Pacific Northwest.
Okay,
And
so tell us about that project.
In the project, so the project's part of our research portfolio, and I'll talk a little bit about the research portfolio later on. The project sprang from a tiny little pilot we did with Pacific Northwest National Laboratories up on the Olympic Peninsula, beautiful part of Washington State. We tested the idea of this sort of transactive energy signal in 100 homes, a municipal water pumping station, and a several megawatt backup generator. And what we found was that we were able to reduce the load on a feeder to 50% of its actual capacity successfully, and B, have customers happy about that. So this idea of sort of a price going to intelligence in the home, not to the consumer, but to a device that the consumer gave permission to, allowed us to really definitely benefit both the consumer, because we were paying them some money, and the grid, because we were able to serve load even though we were artificially constraining this feeder capacity. So from that tiny little beginning, we thought, well, that seemed to work. Let's try it on a larger scale. And we were originally imagining that we would try this on maybe 20 or 30,000 people scale. Well, actually, in large part because of the stimulus, we ended up with a 60,000 customer scale. It's a little bigger than we actually wanted, but it was still scaling up, the idea of scaling up this transactive energy idea to be able to test its viability and actually learn things about it. When you're, the thing that utilities often get lost in is the idea of appropriately scaling things up to where you actually have enough proof you can put it into commercial practice. And people imagine that you can go from an idea to full production overnight. It's not true. Most companies know that. So this scale up allows us to go from 100 customers to 60,000 customers. That's not the population of the Pacific Northwest. At the same time, there's a parallel project going on in American Electric Power Service Territory, AEP, in Ohio, looking at essentially a scale up of the Olympic Peninsula project with a double auction and all the things around transactive energy. So we're going to have sort of 2 contrasting scale ups of this idea of transactive energy. And people are looking at different applications of it. For example, another group in the Department of Energy is looking at rooftop package units,
Yes.
like you would see on the top of a low-rise commercial building, and coordinating the electricity use and the maintenance practices between those units on a particular roof by having a transactive energy signal coordinate their energy use.
They're creating a little virtual power plant.
They're trading
right there.
on the footprint of a rooftop. trading energy between these devices. So the idea is pretty powerful, but it's also really important to keep in mind that we're at the very beginning of understanding it. In fact, just this summer, the very first international conference on transactive energy was in Portland, Oregon. And we had about 150 people show up to begin to explore this idea. So
I was there. It was a very exciting conference.
It was a fun conference.
And so transactive energy has a lot of potential, as we see in the United States. Do you think it has also applicability to other parts of the world, or is it something that's unique to the U.S. markets?
I think it has a lot of applicability in places we just don't even imagine at this point. You know, who would have imagined? We were imagining it on a feeder. AEP is testing it on a feeder. We're actually testing it on a much larger scale grid. But then you have this experiment about a set of packaged rooftop units. So I think we really don't understand. As an example, Portland General Electric has an ultra reliability district around Salem, Oregon. They have an investment in AMI, so smart meters. They have a local customer, Kettle Potato Chips, who has a large PV array. They have some backup gensets, and as part of this smart grid project, they have a 5 megawatt lithium-ion battery. So they're taking the transactive energy signal from Battelle and IBM, and then they're echoing it through this entire district. So it goes down even into individual battery cells to understand whether they should be charging or discharging. So, you know, the exploration of the idea, I think, has lots of stuff yet to go. At some point, it will be commercially viable enough to implement in a lot of places, probably first on microgrids or on rooftop units, you know, a series of things, and then gradually scaling up to grid implementation. You know, what I heard yesterday already was some very interesting challenges in Europe with photovoltaics in Germany and wind in Germany and elsewhere, and conventional power plants, and how you run this grid. And it does seem like the transactive energy concept can help with some of that.
In terms of the timelines, at this point project, how would you see this rolling out? How would you see utilities deploying this as a more of commercialized type of a solution rather than more of the demonstration or proof of concept type of project?
Yeah, see, I don't have much visibility to that. I really don't. Part of the luxury of Bonneville having a research and development program is that we're willing to take risks on things that may not pan out, you know, in the long scale.
Yeah, not everything can be successful.
And we're pretty unique in electric utilities in really managing a research portfolio as if we were General Electric or Intel. We do a professional job of understanding what we're researching, why we're researching it, and we regularly prune things out of our portfolio. So we're willing to take risks around things, and I really don't know where the commercial viability of transactive is. It's an interesting construct. I think it's still got some legs to go, but I fully imagine that as it gets tested in the Northwest and in AEP's territory and gets tested in microgrids like Portland General Electric's, gets tried out in Europe perhaps, and gets tested out in the idea of energy efficiency on rooftop package units as other example, that we'll find things that doesn't work for. And we'll find some other things that it works really, really well. And then, you know, how it gets into a marketplace and whether that takes 3 years or 5 years or 7 years, I don't really have the visibility to.
And as I recall, the project is not just electricity. There's also some thermal storage that's going on as well. Isn't that right, in terms of water heaters?
Yeah, but that's actually in a separate R&D project.
Oh, okay.
Yeah. Part of how Bonneville has managed its research and development is, we try to focus on stuff that matters to BPA. So people should be doing carbon sequestration research. We have a hydro system. We're not doing carbon sequestration research. So we carefully manage what we do R&D on, and then we also carefully manage how we allow projects to progress. And so part of our mandate is energy efficiency. So Being able to manage energy efficiency and water heating is a big resource for us. Being able to bring that into sort of a demand response milieu as well is an important aspect for us. But we have other research topics that we deal with. We
Like what?
are the very next subduction zone earthquake target. Chile, Japan, Indonesia,
Yeah.
these were all horrible
Yeah.
events. And the west coast of Washington and Oregon is really the next place for this. So we have a research project, for example, that's around being able to understand how transformers that are sort of the size of this space and weigh like many times a house could actually move around and stay upright during an earthquake event. Because if the electric system can be easily restored in the wake of an earthquake, then a lot of other systems can be restored on the backbone of having electric service.
Absolutely.
If the electric service cannot be restored, then very other systems are crippled as well.
Well, that's a very interesting and different way than I usually think about the resiliency of the grid. But yes, having a flexible substation that or
Exactly.
transformer that can just kind of rock and roll.
So tomorrow I'm going to show, and actually we'll have a video of this transformer later on, but I'll show a picture of this transformer sitting on what we call base isolation bearings. Now these base isolation bearings are actually in commercial use in high-rise office buildings in earthquake areas.
Well, like San
But
Francisco
nobody's
is
mounted
built
a
that way.
transformer on them. And I can tell you that the people in the electric system don't actually plan on having a transformer move. So the things that are connected to this transformer have to imagine that transformer is going to do the hula. And so, what needs to change and what the mindset is for how that transformer is connected to the grid becomes an important feature of having this not just stand upright, but stand upright in a way that preserves its viability in the future.
We have just like a minute left here. Are there any other interesting projects that you're engaged in, or maybe even to say, how do you determine what makes the grade and what doesn't?
Yeah. So one other project that we have. So the smart grid project, I call that a vertical slice through the grid. It's from wind generation down through transmission and distribution to end uses. But another important aspect of the transmission grid, I call a horizontal slice through it. And for that, we use a technology called phasor measurement units. And the usual method of taking information off the grid is to capture it every 2 seconds in our SCADA system. So that's sort of, imagine the electric
Driving,
system operates at the speed of light. And you're seeing what it's doing every 2 seconds. It's not very frequent. Phasor measurement units take that much more detailed measurements every 60 times a second. So we're moving basically from X-ray to MRI in terms of our
analogy.
understanding of that. And because of that, we're now able to see how wind generators actually behave better than the generators owners themselves can. We're able to see oscillations in the Western interconnection and begin to imagine how we can use that information to manage them, to put some resiliency on the bulk grid. So it's another interesting technology that we've been at now a number of years, and it's looking very promising.
Well, I think we have to wrap up at this point. I could certainly, spend a lot more time chatting with you, and look forward to doing that at future points.
Sure.
But thanks again, Terry Oliver from Bonneville Power Administration, for your time and your insights today.
Thank you.